So at Loam, we do a range of studies across laboratory work, field trialing work, and we work with the best scientists we can. So in this case, we collaborated with Loam to get access to specific expertise and equipment so that we could look at the carbon isotopes and trace them through the plant and into the soil.
I'm a soil ecologist by training. I'm also a biogeochemist. I like to understand how plants and microbes and soil work together to produce the most complex substance on Earth, which is soil carbon. So soil carbon being the greatest storage of carbon on Earth, it's really important to understand how it is built. And carbon is a complex continuum of materials that is always being added to and is always losing materials. So understanding the ecological interactions that lead to building carbon or losing carbon and how they balance together, that is my main motivation for a lot of my research.
What we did was we grew plants in growth chambers and we inoculated the plants with individual fungal isolates. And then we grew those plants for 4 months and continuously labelled the plants with 13C CO2 labelling.
And with wheat plants, we waited to see how the fungi were helping the plant fix carbon or not and bring it from the atmosphere to the soil. And so then after the plants grew and this happened, we used stable isotope approaches to be able to understand the origin of the carbon, and then we also combined that with a lot of approaches to assess the different pools that carbon can be stored in. And we also were very interested in which were the characteristics, and we measured a lot of them, that these fungi had that could be explaining our observations for the soil carbon pools and its dynamics.
As a fungal ecologist, I found it really interesting how different these fungal isolates were from each other. They grew really differently, even on a petri dish. Some of them grew quickly, some of them grew slowly. And then when we added them to soil, they had different ways in which they interacted with the plants, and they had different ways in which they interacted with the soil itself.
So ultimately, soil carbon drives soil health. If you're increasing soil carbon, you're increasing the potential of the soil to hold water, to retain nutrients, to make those nutrients available to plants, and ultimately to increase crop productivity. So an exciting result from this study was seeing up to 9.4% higher soil carbon. And what's most interesting is that there were 20% more resistant carbon. So that means that as carbon's increased, it's more stable to being lost over time.